Now, let's get started by implementing some code to create our very first Resilient Distributed Dataset, or RDD, using PySpark. We begin by initiating something called a Spark session. Think of the Spark session as the entry point for any Spark application. It's what manages the connection to your Spark cluster. Once we set that up, we'll define a simple Python list, a neat little collection of numbers from 1 to 5 that will act as our dataset. Okay, so now let's explore how to create an RDD from this list by using the parallelize function. This function is pretty cool. It takes our list and distributes its elements across the nodes in the Spark cluster, which means we get to enjoy the benefits of parallel processing. Once we call the collect action on the RDD we've just created, we're essentially instructing Spark to fetch all those elements from the distributed dataset and bring them back to our driver program. It's a simple yet powerful operation. When we print the result, we'll see a confirmation that our data has been successfully loaded into Spark. This illustrates just how easy it is to create an RDD and showcases Spark's remarkable capability for handling distributed data right from the get-go. Now that we have our RDD set up, let's explore transformations, starting with the map function. This operation allows us to apply a transformation to every single element in the RDD. For example, if we want to double each number in our dataset, we can define a lambda function that simply multiplies each element by 2. When we apply map to our RDD, we create a new RDD containing these modified values. To see the results, we can use the collect method, which gathers all the elements of the RDD into a list that we can print. And this really showcases the power of transformations in Spark, allowing us to manipulate data efficiently. Next up, we'll implement the filter transformation. This function helps us create a new RDD consisting only of elements that meet specific criteria. In this case, the even numbers. We're going to use a lambda function within the filter to check if each number is divisible by 2. And just like before, to see our results, we'll utilize the collect method. With this, we gain a clearer understanding of how to easily refine our data within Spark, leveraging its intuitive and flexible operations to focus only on the values we really care about. Now, let's see how we can implement the count action in our RDD. This simple yet powerful action allows us to retrieve the total number of elements within an RDD, providing quick insights into our data structure. By calling the count method on our RDD, we can trigger the underlying execution of the transformations that have been defined. Once the computation is complete, the result is stored in the variable countResult, which we can then print out to verify the number of elements in our dataset. Next, we will write a bit more advanced code to transform our RDD into a data frame. To do this, we first create an RDD of rows by mapping each element of the original RDD to a row object. This process structures the data more effectively and prepares it for data frame conversion. After creating this row RDD, we use the createData function to construct our data frame from the row RDD. Finally, we display the data frame using the show method, which allows us to visualize the structured dataset, making it easier to perform operations and analyses akin to working in a pandas data frame. This transition represents a significant leap in how we can handle and manipulate structured data within Spark. Now, let's see how we can leverage SQL capabilities within Spark by registering our data frame as a temporary view. By creating a temporary view using create or replace temp view, we're empowering ourselves to execute SQL queries directly against the data frame. This provides a familiar interface for those who've worked with SQL databases before. In our example, we'll run a SQL query to filter records from the numbers view, focusing on values that are greater than 2. This not only showcases how SQL integrates seamlessly with data frames, but also highlights Spark's versatility in data analysis. When we execute sql-result.show, we get a structured view of our query results, which helps us quickly identify the relevant data points. Next, we'll dive into how to work with data stored in Hadoop, an essential skill for efficiently managing large data sets. To kick things off, we're going to implement the ability to read a CSV file from HDFS. Using Spark's read.csv method, we'll specify the file path alongside options to read the header and automatically infer data types. This approach simplifies loading structured data from distributed storage, and it sets up our data frame df from CSV for further analysis. When we display the data frame with df from csv.show, we'll get a quick glance at the contents, confirming that our data has been imported successfully and is ready for manipulation. Now, let's implement a function to calculate the average value of a specific numerical column in our data frame. First off, we need to import the av function from the pyspark.sql functions module. This gives us access to a bunch of really powerful built-in functions for manipulating our data frames. Using the av function allows us to easily compute aggregate statistics across our large data sets. Next, we'll use the select method on our data frame to specify which column we want to analyze. When we call av column name, we're making it clear that we want the average for that particular column. It's important to note that this operation is executed lazily. What this means, folks, is that it won't actually perform the calculation until we explicitly trigger an action, and we do that by calling collect. This retrieves the results as a list, which makes it easy to print out the average value for us to inspect. Now, let's shift gears and see how we can perform a join operation between two data frames. This is super essential for combining data from various sources. Let's assume we have two data frames, df1 and df2. We can execute a join using the join method, and we'll specify the condition so that it matches rows based on the ID column in both data frames. Just a heads up, this inner join will only return rows where both data frames have matching values, giving us a combined data frame that provides a unified view of the data. This really showcases how Spark efficiently handles relational data connections. Now, let's dive into implementing a linear regression model using Spark's MLlib. First, we need to import some essential classes, specifically Vector Assembler, which helps transform our feature columns into a format that the model can actually understand. And then there's linear regression, which we'll use to create and train our linear regression model. Okay, next up, we'll utilize Vector Assembler to combine our input columns, Feature 1 and Feature 2, into a single output column called Features. This step is super important because, you see, machine learning algorithms in Spark usually need the input data to be in vector format. It simplifies the whole data structure for easier processing. Once we have our assembled feature vectors ready, we can transform our data frame, the one we read from the CSV file, into a training data set. After prepping our features, we move on to instantiate a linear regression object. Here, we'll specify which column is feeding the input features and which one serves as the label for our predictions. Now, when we fit the model to our training data, Spark taps into its distributed computing magic to learn from the dataset efficiently. Finally, we'll see how to apply this trained model to make predictions, which lets us visualize the output side by side with our input data. This whole integration with machine learning really shows how Spark can efficiently process and analyze large data sets for predictive analytics. Now, let's implement the following steps to optimize the performance of our data frame in Spark. First up, we're going to repartition our data frame. This can really boost performance by changing how our data is distributed across the cluster. By specifying just a number, like let's say 4 partitions, we can improve load balancing. This means Spark can utilize its resources more efficiently during computation. This step is crucial because If your data is unevenly partitioned, it can lead to bottlenecks and inefficiencies during processing. Next, we want to check how many partitions our newly optimized data frame has. We'll do this by calling a method that retrieves the number of partitions. This helps us confirm that our repartitioning worked as intended, ensuring we see better performance when we run subsequent operations on the data frame. Now, following this, it's essential to discuss caching. This is a really effective optimization technique in Spark. By caching our data frame, we're making sure that if we access the same dataset repeatedly, Spark will store it in memory. This drastically cuts down processing time for future operations, as the data frame can be pulled from memory instead of recalculated. This can lead to significant time savings during analysis. Handling large datasets efficiently is crucial in data science, and these techniques are invaluable tools you'll want in your Spark arsenal.